Problem 21, the series n equals 1 to infinity of 1 over n to the 4/3 power. I noticed that if I separated this, I could turn it into a p-series problem. So I did 1 to the 4/3 over n to the 4/3, and 1 to the 4/3 is just 1 over n to the 4/3. I now notice that this is a p-series, and p is equal to 4/3, and since p is greater than 4/3 in a p-series, which is greater than, p is equal to 4/3, which is greater than 1, then the series converges. And there we go. All right, 22, n equals 1 to infinity of -3 to the n over n factorial. All right, on this one, I did notice that I have a factorial, and whenever we have a factorial, the ratio test works the absolute best for it, so that is what I'm going to do on this one. I'm going to find the limit as n approaches infinity. First of all, this would be a sub n. A sub n plus 1 would be -3 to the n plus 1 over n plus 1 factorial. So if I took a sub n plus 1, which would be -3 to the n plus 1 over n plus 1 factorial, and I divided it by a sub n, which is -3 to the n over n factorial, I'm going to end up multiplying by the reciprocal, so I'm going to get -3 to the n plus 1 over n plus 1 factorial times n factorial over -3 to the n. Then what we're going to do on this one, I do know that my -3 to the n's will cancel. I'm just going to be left with the -3 up top. And then the n factorial is n times n minus 1 times n minus 2, dot, dot, dot. And then in the denominator, I get n plus 1 times n minus 1 times n minus 2, dot, dot, dot. So everything cancels out except for the n plus 1. So I have -3 over n plus 1. And if I let n approach infinity, I will get 0. So since the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, we know that the series will converge. All right, number 23. We have the series n equals 1 to infinity of e to the 2n over n to the n. And since I saw lots of powers on this one, I decided to do this as a root test. So we'll be finding the limit as n approaches infinity of the nth root of e to the 2n over n to the n. I then decided to separate these, so e to the 2n to the n. There we go. In the numerator, I actually went one step farther, and I made it e squared, e to the n, excuse me. I did e to the n to the nth root, and then I squared it, and then I just left the denominator alone. And then I noticed that the nth power and the nth root cancel each other out. Oops. So I'm just left with e squared. And then down below, the nth power and the nth root cancel each other out, so I'm just left with 1. So I end up getting e, well actually no, I just get n down there, sorry about that. And then if we let n approach infinity, then we will get 0, which is definitely less than 1. So since the limit as n approaches infinity of the nth root of a sub n was less than 1, we know that the series converges. Great, number 24, we have n equals 1 to infinity of n squared over 2 times 2 to the n plus 1 over 3 to the n. You could easily do the root test on this one, but I just decided to do the ratio test. But either test would definitely work. So this is going to be my a sub n, and then my a sub n plus 1 will be n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1. All right, so we're going to be finding the limit as n approaches infinity of a sub n plus 1, so the n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1 divided by a sub n, which is going to be n squared times 2 to the n plus 1 over 3 to the n. So I'm going to multiply by the reciprocal, so I'm going to get n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1 times 3 to the n over n squared times 2 to the n plus 1. Okay, so let's see what cancels here. Okay, I know nothing's going to cancel with that n plus 1 squared at all. Okay, and then let's see with that 2. If I have 2 to the n plus 2 and 2 to the n plus 1, I'm going to end up with 2 in the numerator. And then down in the denominator, since I have 3 to the n and 3 to the n plus 1, I'll be left with a 3 down below, and I'll also be left with the n squared. And so from here, I'm just going to rewrite this as 2n plus 1 squared over 3n squared. If I were to plug in infinity, I get infinity over infinity, so I get to use L'Hopital now. So I will be finding the limit as n approaches infinity. If I take the derivative of this, it will be 4 times the quantity n plus 1. I use the chain rule on that one. And then on the bottom, I'll get 6n. And let's see, I'm just going to make this 4n plus 4 over 6n. If I plug in infinity, I once again get infinity over infinity. So L'Hopital once again. So get the limit as n approaches infinity. Up top, I'll get 4. On the bottom, I'll get 6. That reduces to 2/3. So I got a limit that was less than 1. So since the limit as n approaches infinity of a sub n plus 1 or a sub n is less than 1, we can say that the series converges. All right, one last one. We have n equals 1 to infinity of n plus 1 over 2n plus 1, all raised to the n power. This is a perfect one to do the root test on because it's got a power. All right, so we will take the limit as n approaches infinity of the nth root of n plus 1 over 2n plus 1, all raised to the nth power, and obviously the nth power and the nth root are going to cancel each other out, so I'll just be left with n plus 1 over 2n plus 1. If I plug in infinity, I'll get infinity over infinity, so I get to use L'Hopital's rule. And if I do that, I'll find the limit as n approaches infinity. The derivatives of the numerator and the denominator would be 1 over 2, so I get an answer of 1/2. That is definitely less than 1. So I can say since, let's call this a sub n, make sure we always clarify that so we know what we're talking about here. So since we have the limit as n approaches infinity of the nth root of a sub n is less than 1, we can say that the series once again converges.